Hello, wonderful people. Welcome to Cosmology Talks. Today we have Wendy Freedman, who is a professor at the University of Chicago, and Barry Madore, who is a research astronomer at the Carnegie Institution for Science. They're talking about the latest results from the Carnegie-Chicago Hubble Program, which is one of the two main groups currently measuring the expansion rate or Hubble parameter of the universe using distance ladders. None of this probably needs motivation. The Hubble tension is possibly the most tantalizing thing in cosmology right now, and Wendy, Barry, and the rest of CCHP have been leading experts on the measurement of the Hubble parameter for a long time. So welcome, Wendy and Barry. Do you want to start by telling us briefly about your paper?
Oh, thanks for having us. As the title says, we're presenting a status report on our Chicago-Carnegie Hubble Program, and it's a project we're very excited about based on JWST, James Webb Space Telescope data, using three independent methods for measuring distances to galaxies. We tie those into more distant type 1a supernovae, and then we can get three independent measures of the Hubble constant with the aim of being able to average over constrained three different methods and get a more robust error estimate, systematic error estimate.
If people are thinking of this talk or your paper 6 months from now, and there are only two things they're able to remember, what would you want those two things to be?
Two most memorable things I think I want people to walk away with is one, these JWST data really are spectacular. It's an enormous step in accuracy in terms of getting at systematics, which are the bane of the extragalactic distance scale. And as the title says, this is a status report. I think JWST is going to have a lot more to offer in the next few years, but it is an exciting first step. And the second is that the Hubble tension now has achieved a status of an extraordinary significance and the sort of 1 in a million 5 sigma gold standard. And I think as the phrase goes, extraordinary claims require extraordinary evidence. And we aren't seeing now extraordinary evidence for a Hubble tension.
Yeah, I guess you'll get into the results soon enough, but you have your three different methods. I guess your Cepheid measurement, it's not necessarily in tension with the others, but it certainly seems to be consistent with the other group, the SH0ES group. Would your thinking be that there is some unknown systematics in the Cepheid process of doing the distance ladder?
I think what we're seeing is that there is some unknown systematic. I would say at this point, maybe we don't know exactly where it is. It currently looks like the Cepheids are the outliers because the other two methods, the JAGB and the tip of the red giant branch TRGB, are agreeing extremely well. And our Cepheid distances do agree with the other group, the SH0ES group. But as we'll see, the Cepheids do have additional complications and challenges, and some of which the JGB and TRGB methods don't suffer from.
Cool. So yeah, let's get into some of the motivation now. Why you're doing this? I think in 2024 the Hubble tension doesn't need that much motivation, and so measuring the Hubble parameter doesn't either. But perhaps you can also go into some background of why these three methods are the kind of gold standard methods at the moment.
Yeah, a little bit of motivation of how we started this JWST proposal in cycle one. And what I'm showing here are measurements of the Hubble constant over time, that year of publication. And starting essentially with the Hubble Key Project, which we finished in 2001. So Barry and I have been working in this field for a very long time. And we used Cepheids with the Hubble Key Project to calibrate a number of methods and to measure the Hubble constant. And the fundamental philosophy of the Key Project was, let's not put all our eggs in one basket. And that's our philosophy here again with the Chicago-Carnegie Hubble Project. The Cepheids, as you can see, shown in red, have been very consistent over the last 20 or more years, almost a quarter of a century now. And they give a value between 70 and 74. And what has changed, I mean, the value hasn't changed, but the uncertainty has changed. And now to the point where, other groups are claiming that there's a 1% measurement of the Hubble constant. And that, of course, is what leads to the tension, because the cosmic microwave background observations are giving a lower value, more like 67. But what I'm showing in the bottom plot is, again, these same observations. And this, by the way, is a database that John Huckra put together very early on, and it's been maintained and updated by Ian dear. And you can see, again, the Hubble constant measurements as a function of time, and they're divided here into decades. And if you plot the histogram of those various values, they really do agree in the mode of that distribution hasn't changed very much. It is about 69 kilometers per second per megaparsec, which is interesting because I think we've started to talk about the Hubble tension and to think about measurements of the Hubble constant as there being a bimodal distribution. There's a 73 and there's a 67 and there's just not much else. And that's not the case. And in fact, the Cepheids do lie rather high. And you have to wonder again, as we worried about with the key project. You recall when we started the key project, we were arguing about values between 50 and 100. That's pre-key project. That was the situation we were in. And it was, of course, systematics that those are the hard things to overcome. And so our interest was in, again, testing the Cepheids, because any one method will have its own set of systematics, both known and unknown. There may be things we just don't know yet about Cepheids. And so that's why we aimed to measure more than one method for the same galaxies. And that's the point. Let's measure the same galaxies with the same instrumentation, the same filters, same calibration, and see how well they agree, and whether or not, will all three agree really well? Will there be a wide dispersion? Will two agree and one disagree? We didn't know. And we started out the project completely blind, I should say, which is that different groups within our group didn't know what the others were doing or finding. They added a random 0 point to all of the photometry catalogs and didn't know where anybody else was measuring things. So that was interesting. In the end, only one of the methods made it all the way through blind for reasons we can talk about. But the idea was to do this as separately as possible without any knowledge of where it would go. And our view is that you need several methods that all have very high internal precision, because that's where you get to understanding, again, the accuracy, that where are the systematics. And clearly every method will have its own systematics, and they will be different, which is important because then you can combine them and average over the systematics, and that's how you'll get a more robust overall measurement.
The other key point is that they'll have their own unknown systematics, so you can't just kind of add your own plus or minus X. If you don't know what X is, you can't sort of quote it. If it's an unknown systematic, you don't know how big it necessarily is.
Yeah, and that's been the problem really all along in measurements of the Hubble constant. It's not as if we're doing a laboratory experiment where we can go in and turn knobs and test for systematics. We're using these astrophysical objects that are hundreds of millions of light years away. In many cases, some of them involve explosions, and we're trying to use their properties to gauge distances. And the cosmic microwave background observations have really set a very high standard, because if the standard model is correct and the fit to the acoustic spectrum, which it's such a beautiful fit. I mean, the precision is better than 1%, right? So that hasn't been achievable in the local distance scale. And I would say, and I know Barry will agree, we just haven't reached that in the local distance scale yet. It's much too challenging. And if you think of it, we're measuring distances locally. We go out to the realm where we can measure distances with Hubble and JWST, and then even farther out to the supernovae. And if you want a 1% H0 overall, you got to make sure that all the rungs of that ladder, that all of the systematics are understood at that level. Even doing photometry at 1% accuracy is extraordinarily challenging, let alone when you're pushing the limits of a given facility or detector.
But I think it's worth pointing out that if two of those methods, in fact, do agree in their 0 point, and both of them have low scatter against one another, then that tells you something really important, because the other one, whichever one it may be, it sort of has the finger pointed at it. I mean, why is it standing off from two other things that have nothing in common for most of their systematics, and they do agree?
So I just wanted to note, we've just posted a paper this week that is the paper that describes our Hubble constant results. And last week, our graduate student, Abby Lee, posted a paper on the JAGB method, which she will talk about at some point soon. And I just wanted to mention the three other members of our group: Taylor Hoyt, who's at Lawrence Berkeley Laboratory, and In-Sung Jang, he's a research assistant here at University of Chicago, and Kayla Owens, who's a graduate student here at University of Chicago. And so there are other papers coming. So there'll be a paper on the tip of the red giant branch led by Taylor, and the Cepheids by Kayla, and also in preparation is the photometry and how the calibration has all been done by In-Sung. And Barry has an additional paper in preparation about the Cepheid method.
The talk by Abigail Lee should be out next week on Cosmology Talks. Am I right that that paper that you've listed there, that's the first time that the JAGB method has kind of reached maturity to the point where there is a Hubble value quoted in the paper?
That is correct. It was actually a method that was developed now in the early 2000s by Nikolaev and Weinberg. They applied it to the Large Magellanic Cloud, and they were looking at the geometric tilt of the cloud. And Barry and I, it was actually a pandemic project, looked at data for other galaxies and realized this was a really very successful distance indicator when we compared it to other published values that had come from the tip of the red giant branch. And so, yeah, this forms the bulk of Abby's thesis. She's now extended it to JWST, and we also had looked at earlier Hubble data.
And it actually has the smallest statistical error of your three methods, doesn't it, as well?
It does. Well, it's essentially comparable if you use the same size sample of supernovae. So, it's comparable.
In terms of its own precision, there are thousands of these JAGB stars in any given image. So if you're playing the divide by square root of n, they really smash the intrinsic scatter down to something that's negligible.
So here are our galaxies. These are the first target galaxies that we have. We plan to get many more with JWST. And it's probably a little bit difficult to see the red squares, which are the positions of the NIRCam, the camera that we're using on JWST. But there are two red squares in each of these, and the outer ones are where we're measuring the tip of the red giant branch out in the halo. So the thing to be said is that the Cepheids live in the disks of galaxies. They are young stars. That's where they're located. We have no choice but to measure Cepheids in the high surface brightness regions, the disks of galaxies. And there are TRGB, of course, stars. There are red giants, and there are asymptotic giant branch stars in the disk, but they also are located TRGB in the halo and the JGB in the outer disk and also somewhat in the halo. So one of the advantages of the TRGB and also JGB is that you can make these measurements in regions where there's essentially no dust, and the crowding or overlapping of stars that occurs in the disks of the galaxies that makes photometry very challenging because you have a limited resolution, a pixel size on your detector. And the farther out you go, the more galaxy you have, and your more distant galaxies that are contained in that pixel. So separating your Cepheids is it's a challenging task. You need accurate colors, and you need enough resolution to do that. So you need the colors to correct for dust, you need the colors to correct for metallicity of the Cepheids, and you need to do artificial star corrections. That is, we put in stars whose luminosities and colors we know, and then extract them in the same way as we would for a Cepheid, a real Cepheid in the frame. And you do that in a statistical sense. We do 1,000 stars for each of the Cepheids, and then you get some idea of what the uncertainty is. But it's only a statistical correction. And if you don't get that right, you don't get the dust correction right, you don't get the metallicity correction right. So those effects are covariant, and they worsen with increasing distance. And that's why the JGB and TRGB offer an opportunity to make measurements that aren't as challenging in that sense. So this is now an example of a Cepheid in a galaxy at a distance of 20 megaparsecs. This is NGC 7250, and it's a Cepheid that was discovered using Hubble, and in the red circle. And you can see there's a lot of background stars, and the light coming from the Cepheid is really very faint. It's very hard to see where that Cepheid is. It was discovered in the optical. That's where the variability of Cepheids is greatest. And you follow them up in the infrared. This is, technique standard for years. Barry and I developed in the 1980s, in fact, for how to measure the reddening to Cepheids, or correct for the reddening. And if you then go to JWST, you can see at a glance, there's the same Cepheid, how much better JWST does. It's got 4 times the resolution, as I said, and it's 10 times the sensitivity. And doing photometry, measuring the brightness of that Cepheid with JWST is a lot easier and more accurate than with HST. Now, HST has done wonderful things. I don't want to criticize HST. It's been the workhorse for finding Cepheids. It's what we use for the key project. It's what SH0ES uses. And when you have high signal to noise data, it's a spectacular machine. But pushing to the infrared doesn't have much infrared sensitivity. And when you're moving out to farther and farther distances, your signal to noise is low and the crowding becomes worse. The resolution is worse. So it's just pushing the facility probably beyond where you really can get accurate photometry, but that's where JWST comes in and where it can help.
And I presume once you've introduced how Cepheids are used, the reason why you want to go to the infrared will become apparent at that point.
And let me just say briefly, so if you go to the infrared, the effects of dust are minimized, and the effects of dust are much larger in the blue. The effects of metallicity are lower, and so there are enormous advantages in terms of systematics to going to the infrared, near infrared. Here's another example of a Cepheid at 20 megaparsec, same galaxy. That's the HST image, and again, you can see the huge amount of other light that is in the frame. Separating the Cepheid accurately is a challenge. And then here it is with JWST. And again, measurements with JWST are just much cleaner and higher accuracy. So I just want to point out that distances greater than 20 megaparsecs, then in the same area, there's 8 times more area contained than you have at 7 megaparsecs, which is the distance to NGC 4258, which is our calibrator. And if you go to 40 megaparsecs and a quarter of the sample is beyond that, then it's an area that's 33 times larger than 7 megaparsecs. So you're putting an awful lot of galaxy in that same area. And getting accurate photometry again is challenging.
And if I understand the point you were making here correctly, it was that when we are looking at NGC 4258, the amount of crowding to the Cepheids in that galaxy, because it's so much nearer and we have better resolution of it on an absolute scale, is much, much less than when we're looking at the other ones. So therefore, the kind of Cepheids that were being calibrated had less crowding than the Cepheids that are then being used. So that might be some sort of possible origin of a systematic.
That's correct. And the SH0ES sample even has a galaxy at 80 megaparsecs, right? So, and as you go farther and farther, you're just getting more and more of the area of the galaxy into your pixel. And so it just becomes much more challenging. Just a few other examples, but I just want to also point out that in the optical, so the left-hand panel is essentially the V band here with HST, and then the I band is the second panel, and then the JWST observations are in the third panel. So you can see you can resolve the Cepheids pretty well in all 3 of those. But when you go again to the infrared, and most of the distance information is coming from the infrared. Correction for reddening comes from the optical, but you need accurate near infrared data to get the distance. And that's just tough when you're going out to these very distant galaxies. Nearby, Hubble, when it's high signal noise data, it does superbly.
Yeah, I mean, as a naive non-observer looking at that 4th column, one, I guess, has to assume that nothing else inside the red circle is acting like a Cepheid, because otherwise you just have absolutely no idea. Because you're not resolving a point source at all within that, but I guess the periodicity of the Cepheid will be periodic, but everything else inside that circle won't be. So therefore, you know what is coming from the Cepheid and what is not coming from the Cepheid.
Right. Most likely you don't have 2, but you could have a binary star, but also you don't know what's behind the Cepheid, right? So there could be a star, many stars, a cluster of stars. You don't know.
Sorry, just to belabor the point a little bit. When you say you don't know, I guess you do have the images on the left, but maybe there's something that's in the infrared, visible in the infrared, but not visible in the optical. Is that the concern?
Well, both, right? But you could also have something that's behind the Cepheid that you would know nothing about. It's contained within the point spread function.
Even on the higher resolution images on the left, you mean?
It potentially for the more distant ones, but yeah, more likely with the lower resolution in the infrared.
Everybody realizes that because in the infrared, you want to go there because of lower reddening, but at the same time, the amplitudes are getting smaller, which makes them almost undetectable in terms of variability. So you don't want to go searching for them in the infrared. And the sad thing is that JWST does not have optical bands where you can do the search effectively. And so we're probably not ever going to see a search for Cepheids using JWST.
So the images you've done with JWST are directed at lines of sight where you previously knew there would be Cepheids.
That's right.
Exactly.
So now we get to the 3 distance indicators. So for those who aren't familiar, probably most people are familiar with Cepheids, but the other 2 methods I think may not be as well known. So on the left, there's the plot of luminosity versus temperature, or in observational terms, a color magnitude diagram based on JWST data. So so hotter stars are to the left. And we're looking at the outer region, the halo of the galaxy, the red points, and the inner disk region are the blue points. So you can see the Cepheids at the top. Those are the brightest of the distance indicators, and that's the so-called instability strip where the Cepheids lie. And then next in brightness come these carbon stars, the JAGB stars, which are still quite luminous in the near infrared. And then you get the giant branch in red, and then stars at the tip of the red giant branch we'll describe more in a moment. But the beauty of this is that you can do them all at once in the same galaxies with the same detectors, etc.
Before we leave the composite diagram, I think there's something very important, that to find the use Cepheids, you need the time domain. You have to be able to find them through their variability, observe them enough times that you map out their light curves and get periods. You might notice that this color magnitude diagram has no time tag in it. The carbon stars are there in a single exposure. They are identifiable by their color. Color is independent of distance. It's something that you can use and immediately use them from a single epoch. The same thing is true of the tip of the red giant branch. It's a single observation of the single epoch. The color is where you find them, and the feature that line is showing you is the distance indicator. So the Cepheids are more demanding. The tip of the red giant branch is particularly wonderful in the sense that actually the theorists were way out ahead of us. They knew that there was this feature in the color magnitude diagram based on laboratory physics and stellar evolution, that when a low mass star leaves the main sequence, the reason it leaves the main sequence is that it's burned all of the hydrogen in its core, and it starts to contract, and the pressure increases in the central regions, and the pressure and density becomes so high that the core becomes electron degenerate. So it has a phase change in the stellar structure that's holding up the star.
So the feature that Barry is referring to, if we look at the one on the right, for example, so this is NGC 4258, in fact, and so you're plotting the luminosity as a function of the color of the star, and the black line indicates where this so-called core helium flash is, where the star can burn helium and it settles down onto the horizontal branch. And so what we do is measure the luminosity function, which on the right-hand side of the plot is the number of stars there as a function of magnitude. And then we use an edge detector or maximum likelihood method, doesn't matter, they agree very well, to determine where that edge is. And it's difficult to see by eye, but it's an unmistakable feature that we can measure. Again, we can do artificial star experiments, and we can see how well we can recover the stars and measure that peak. In the infrared, the left two plots are from the J band. All of these data now are from JWST. The right is archival data. But there's a color slope in the infrared, which we can take out. But it's, as Barry says, very straightforward, very simple. You measure a luminosity function, you measure the peak, and the photometry, as we were discussing earlier, is very simple because these stars aren't crowded. There's no dust. The metallicity correlates directly with the color. So it's a very simple, easy to apply technique when you do it in the halo.
Can I just maybe try and give a naive outsider summary of the TRGB? So the idea is that there is this peak luminosity that if the physics tried to make it more luminous, there'd be a phase transition in the star so that it can't actually get more luminous than that. And therefore, when you're looking at galaxies that are further and further away, this tip of the red giant branch, in the sense that the tip luminosity, you can't get more luminous than that, will be at a different relative luminosity as measured by us. And therefore, if it's lower down, it must be further away. If it's higher up, it must be closer. That's kind of the broad overview summary for someone who's never encountered TRGB before. Is that a fair description?
Yeah, that's fair.
So just with the Cepheids, the one sentence overview is that there is this period luminosity relation. So by measuring the period of the Cepheid and how its luminosity is changing with time, that there is a direct relationship between that and the intrinsic luminosity of the Cepheid. And therefore, as you see the relative luminosity change given a certain period, you can tell whether the Cepheid is closer or further away, because the period is kind of telling you what the absolute luminosity should be once you've calibrated it and fit it to a particular empirical function.
The classic textbook description is a period luminosity relation. That's what Henrietta Leavitt discovered. But it actually is a period luminosity color metallicity relation. So to get the colors, you need to have the dust correction. And to get the metallicity, you need to know how does the luminosity vary with metallicity. And that's something that's still not well understood. There's still quite a considerable amount of discussion in the literature about how strong a correlation it is.
That scatter in any given PL relation is not noise. It's deterministic, it's physical. And you have to be able to, as Wendy said, first get the reddening in order to get the color, in order to get the distances. And so if you're looking for simplicity as a criterion, Cepheids are the most complicated of the three.
Is there like a one sentence, I presume there's probably a Wikipedia article on this anyway, but is there like a one sentence physics explanation of why there is the period luminosity relationship that you can just give?
Well, the simplest way of stating it is the stars are actually pulsating. Their other atmospheres are moving in and out, and it takes longer for the larger Cepheids to go through their cycles. So there's, just a one-to-one correlation between log of period and log of luminosity.
There's also something called the p-root rho relation, which is in most physics books, that the density of an object will tell you its fundamental mode of pulsating. Okay, so the density is a function of the radius of the star and the total mass of the star. And so you do stellar evolution, you put in a mass, you put in a radius, you get its period. Okay, so Cepheids come in various masses, and the low density ones have the longer periods. That's your physics answer. It's like bells. I mean, big bells have different frequencies than little bells.
I'm just going to say just a couple words about Cepheids. More well known, the period luminosity relation here. These are the archival data. We reanalyzed the V and the I data from Hubble, the optical data, and the yellow points are the new JWST data. What you'll notice, and we haven't talked about, is that the amplitudes we've mentioned of the Cepheids are larger in the optical, but the same thing happens with the period luminosity relation. This is a temperature effect, and you have less temperature sensitivity in the infrared. So the scatter in the period luminosity relation goes down.
Okay, and now let's move on to JAGB.
There's a part of this that is purely phenomenological. When the two-mass survey of the sky was undertaken, as Wendy said, Nikolaev and Weinberg looked at all of the populations of stars in the Large Magellanic Cloud, and they found this feature, this clumping of stars that are distinguished by their very, very red colors.
So we should point out there's this blue region, shaded region in the lower right plot that is indicating this region of color and also the where these stars reside.
So it's a feature that there's a subpopulation that have a particular color.
Yes, and they turn out to have a very small scatter.
I mean, there are physically understood, albeit really difficult, physics of these asymptotic giant branch stars that at a given mass, they will dredge up, bring carbon up from the interior and dump it into the atmosphere, and they completely change the color and structure of the outer part of the star. They become carbon stars. And so there's another mechanism which cuts that mechanism off and prevents stars that are higher than a certain mass from bringing up carbon because they're so hot they burn the carbon before it gets to the surface. So there's this mass guillotine effect which focuses and funnels things out in mass, which in turn is luminosity. And the feature is that identifies them is their carbon in the atmosphere, which makes them red. So they become really, really powerful distance indicators for intermediate age stars. And you see them in the thousands. And their intrinsic dispersion is around 0.2 of a magnitude. And you can imagine 0.2 divided by the square root of 1,000 is a very, very accurate distance indicator.
I guess we'll go into more detail on this in a talk on the channel next week with Abigail Lee, who was the lead author of this new JAGB methods Hubble measurement.
Yeah, I don't want to dwell on this. I just want to point out that we put a lot of effort into doing the data analysis and redoing the data analysis and independently using different methods for measuring the photometry and checking with space telescope aperture corrections. I mentioned we started out blind, and we tie into 2 supernova samples, both the Pantheon Plus and the Carnegie Supernova project, and I'll say more about that in a minute because that's the project we've been involved in. And I've already mentioned that we use NGC 4258 as the local anchor that sets the calibration for our distances. So lots of tests, lots of artificial star tests, lots of really making sure that we were happy with our photometry. And I should mention that we reanalyzed the data in the archive. So that hadn't been done before. Everybody has been going from the process data forward. Now we get to a comparison of the distances that we've measured as part of this project. So I'm comparing here distances. We're not yet talking about the Hubble constant. And the top plot is a comparison of distances using the JAGB method and the tip of the red giant method for galaxies in common. And you can see this really nice correlation between the distances. The blue points show the one-to-one correspondence, and the red points are the residuals from the fit, which is the slope 1-1. And the distances agree to better than 1%, which is spectacular agreement. These had nothing to do with each other. And, as we saw, very different physical mechanisms that are giving rise to the JGB stars and the TRGB stars. And the scatter is also very low at the 2% level. And that's really new.
So they are confirming it. They're confirming each other, all right? Not only in 0 point, but because the scatter is so small, all of the unknown unknowns in the 2 distance determination methods, in the TRGB, which we haven't thought of, or something different in the JGB, is in the scatter. And the scatter is really small, which tells me that we haven't left out very much.
One thing to be said is that they share the uncertainty in the 0 point, that is NGC 4258. So if there turns out to be some systematic, that's currently estimated to be 1.5%. But if there was some systematic in that determination, everything that we have done would slide with that. And that's true of the other group too.
But the scatter would not change.
The scatter would not, no. And the relative comparison would remain because they have the same calibration. So the middle panel now is comparing the TRGB and the Cepheid distances, and it's not a bad comparison again. I mean, it's 2.5% offset, which is pretty good for extragalactic distances. But the scatter is larger. It's more like 4%. So they're not agreeing as well with as the JGB and TRGB distances are. And then the bottom plot compares the JAGB to the Cepheids, and again, it's larger scatter and larger offset. So the better agreement does come with the JAGB and the TRGB, but really, in historical terms, this is good agreement for distance indicators. But the Cepheids are the outlier right now.
When you say the 0 was the same to JAGB and TRGB, is the 0 to the Cepheids here different then, or also the same?
No, all the same calibration, which is the beauty of this, right? We're comparing everything in a relative set. They're all fixed to the same absolute calibration, and then we just do the relative comparison amongst the methods. So these are the same galaxies. And the point to be made here is that this is before we go to determination of the Hubble constant. We're talking about direct measurement of distances here. And this is where we're already seeing a discrepancy. So it's important for us to understand the source of that discrepancy before we can start to claim that there's new physics, because the JGB and TRGB stars are not going to be giving the same result as the Cepheids. They're going to come in lower. So this plot shows the comparison starting from the ground. So these are data that were taken with ground-based telescopes, and starting at 50 kiloparsecs, the Large Magellanic Cloud, up through the JWST data, and the blue points on the right, and those are up to 23 megaparsecs now. So that's a factor of 50 in distance, and they're holding up pretty well. The calibration of both of those looks pretty encouraging. And again, we just haven't seen this kind of agreement one-to-one. We haven't had precision distances to the same galaxies that we can do this for until we've developed these methods recently.
And I might note that the 0 point for the panel on the lower left is determined independently of the 0 point that was for the panel in the upper right, because the upper right is 4258 and the stuff in the lower is from the LMC and SMC, where they also have their own geometric 0 points established from detached eclipsing binaries. So there's a confirmation.
The bottom left plot here is just for visualization on this slide. It isn't actually being used for your results later on when you say what the Hubble parameter is. So it's just the JWST.
Yeah, these other galaxies don't have type 1a supernovae in them either. So, but it's just a comparison of the methods and just showing how well it works over this large range and distance. And as Barry said, there are two other geometric anchors that lock in the ground-based data, and they just agree extremely well with the new JWST data. So something is working here.
I guess the other point is that if somebody wants to change things at the distance of 4258, this diagram will fall apart.
They'd have to do it also in the Large Magellanic. It would have to be the same mistake in both, I guess.
Yes, they would have to coordinate it locally and distantly in the same direction by the same amount.
Now we get into where we have to tie into the type 1a supernovae, where we're going to measure the Hubble constant. And this is one of the things that now I think is limiting all of us who are trying to measure the Hubble constant. And there are sort of 2 points to make from this. One is the sample is small. So this is the sample of galaxies that have Cepheid distances and have hosted type 1a supernovae. So there are about 40 galaxies in this sample, 37 galaxies, 42 supernovae to be exact. And you can see, so I've actually marked the distances in here. So there's the distance modulus on the bottom, and then the absolute magnitude of the supernova. So this is the peak brightness of a supernova at its maximum before it declines. It has this rise and then it declines. So measuring that luminosity at the peak. And so we're going to, the nearest ones are sort of just less than 10 megaparsecs. That's NGC 4258. No, that's M101, sorry, M101. And then 4258 doesn't have a supernova. And then going out to this point here at 80 megaparsecs, that's the most distant one. So you can see there's scatter in the absolute magnitudes, and also there appears to be a slope. So our sample, our initial sample, we set out to measure the closest galaxies in the SH0ES sample that had Cepheids, because they have the most reliable distances, they have the most reliable supernovae, they're the brightest, and so the high signal to noise. And we wanted to make sure that we weren't getting into a realm where crowding and blending of images had been a problem. And we wanted to make sure that we could measure accurate distances with JWST. And so the fact is that if you use the nearby ones that have the smallest errors, you get a lower value of the Hubble constant than if you use the full sample, which is worrisome. That is a potential systematic that we need to understand. And that will require more JWST data to get to the bottom of that.
And that's the 71.3 versus 73.0.
That's correct. So it's not simply a matter of numbers of objects, systematics, right? So if you make measurements and you make them over and over and over again, statistically, you can decrease your error just by making more measurements. But if there's a systematic, doesn't matter how many times you measure it, you're going to be off. And so we really do need to understand this. It's, I think, a big concern. And it's one of the problems of having a small sample, and the fact that supernovae are rare, and the distances of the farther galaxies are hard to measure. They're we've seen the images, JWST versus Hubble, and what I showed earlier were for galaxies at 20 megaparsecs. We're not talking about the ones at 40 or 60. So the bottom plot, and I won't dwell here, just to point out that these distances again are hard, and if you compare the distances that have been measured, in 2016 compared to 2022, some of those changed by 0.3 of a magnitude. That's 15% in distance. So these distances are hard, and is there still a question about these further objects, beyond 20 megaparsecs? I think that, we don't know yet, but JWST is going to help us get there. We're talking about very subtle differences too, and they have a big impact on the Hubble constant. Move on now to the supernova end of things for our project, and we're using supernovae that have been measured as part of the Carnegie Supernova project. This is a project I was involved in for many years when I was at the Carnegie Institution. We paid a lot of attention to observing these supernovae with the same detectors again, the same filters. We monitored the flux that was coming onto the detectors yearly to make sure that there was no drift in the calibration. And we put a lot of effort into, this is a follow-up project. So it wasn't a project to find the supernovae, it was people had found them, and we did multi-wavelength photometry, making sure that we caught the supernovae before their peak, so that we could measure the peak very well. And there were two phases, Carnegie Supernova 1 and 2, I've just shown in different colors here. But this is the sample, and I do think it's important that a consistent calibration again. So we have a consistent calibration of our Cepheid, JAGB, and TRGB with the same detectors with JWST, and we have a consistent calibration for the supernovae also. So the Pantheon sample, it's a phenomenal sample, but it's 18 surveys that have been put together, and that's just, it's hard to do and bring all the calibrations onto a consistent 0 point.
I guess the Dark Energy Survey recently released like 1800 supernovae. Why not use them if it's a factor of 10 more supernovae?
So the question is over what redshift, and you want that intermediate redshift, right? So the dark energy, they're trying to go out way farther, right, where you can actually measure the acceleration. This is still local in terms of, we're going out to redshifts of 0.01 to make this measurement. So, not to go too much into the weeds, but we do an MC analysis. We've used two different codes to do that. We're fitting 9 parameters. I've shown one example here for the tip of the red giant branch, and we do this for all of the methods, and that's how we have measured the various Hubble constants that we get from the different methods. And again, I don't want to dwell on the details here, except to point out, we've done different kinds of tests cutoff in redshift, because the low redshift ones introduce more scatter into the calibrators. We've done using different codes for the MC analysis. We've done the H-band data. We've looked at the Pantheon data. We've combined the data. We've looked at Cepheids with metallicity, without metallicity, and so on. So it's not a very large range that we get differences in the Hubble constant under those different conditions, which is good. It's fairly robust. But as we've seen, we get different answers for the Cepheids from the JAGB and TRGB. So the values, the final values that we adopted for TRGB here is 69.85. For the JAGB is 67.96 here, and then the Cepheids are 72.05. And I'll show you in a moment how we've combined them, did a Bayesian analysis to combine them, and we get a value of 69.96, and the statistical uncertainty is 1.05, and the systematic is 1.12.
Your plus or minus on your Cepheid measurement here is larger than what SH0ES quote. Why? Is it that they've got more statistics, or you're being more conservative in terms of your error estimate? What is the physics or statistics that's causing that?
Yeah, it's both. They do have more data now, so statistically they have a larger sample, and also we have been more conservative. You make various choices, and if you have a very small uncertainty, say in your metallicity correction, that gets factored in. We also find that there's an effect that comes with what period you choose to cut at in the calibrator for NGC 4258. That also will improve with time, we believe, when we get a larger sample, which we will have in future. So we have deliberately erred on the side of being conservative. And we've also separated the statistical and the systematic uncertainties. And we think that's important because it gives you a sense of where improvements could come or where you need to improve. And, if you diagonalize your matrix, you're looking at the off diagonal elements, covariance, that kind of gets hidden. And so we tend to prefer explicitly showing where the statistical and where the systematic uncertainties are coming in. But you're correct, it's both. It's we have smaller samples, and also we have been more conservative.
Our 0 point for the Cepheids is only JWST because we're only using 4258. The SH0ES project has several other 0 point calibrators, which brings down their systematic error, which we are not able to take advantage of.
And just to add to that, so we did a study in 2019 for the tip of the red giant branch where we had, I guess 2019 and then through 2021, but 4 calibrators. We had the LMC, SMC, and then 4258, and the Milky Way. And that agrees very well with what we're finding with JWST. So that's it's a trade-off. They have more anchors. We have more of the middle rung. So we have Cepheids, TRGB, and JAGB. But again, as Barry says, the one of the reasons why their uncertainties are smaller is that they have 3 local anchors. And right now, the Cepheids, all of these methods, the stars are too bright to observe the Cepheids, JAGB, and TRGB stars in the LMC and the Milky Way with JWST. It's too big a telescope. it's both an advantage to have a big telescope and a disadvantage in that sense. They're too bright.
One would tell 2 different stories looking at this table with if one knows about SH0ES or doesn't know about SH0ES, I guess, because if one didn't know about SH0ES, one would just say, okay, all 3 of these measurements are consistent with each other when you look at their error bars, and great, combine them all. I mean, and arguably also consistent with Planck, even like 72 plus or minus, 1.85 and 1.85. Yeah, it's just a scatter out. But then if you know about SH0ES, then the higher value of your Cepheid one becomes much more interesting. It's like, okay, we already know about this other Cepheid measurement, which is very high. So then it starts to look like, yeah, you're seeing the same thing in your Cepheids as they're seeing in their Cepheid measurement, I guess.
Well, we're consistent with their Cepheid measurements, but you can also see that the Cepheid measurements for the more distant galaxies, the crowded galaxies, whether or not those uncertainties are as small as that error estimate might lead you to believe, I think, something we still need to understand a little better. And I think we just don't have enough JWST data yet to unambiguously determine whether the uncertainty is that small.
A variation on your theme, Sean, is that if the original value of the Hubble constant had been derived only through the tip of the red giant branch, and it came up with 70. And then suddenly Cepheids came along and came up with this much larger value. People might start to wonder, well, how good are those no kids on the block, those Cepheid guys? Should we be looking at them with a little bit more detailed analysis? And the answer is yes.
I suppose the story would be even stronger if it was TRGB and then JAGB came along second and then Cepheids came along third. It would be a much more compelling even then.
And as I said earlier, the discrepancy is already arising before you get to the analysis of the Hubble constant. It has nothing to do with the supernovae. It's in the distances to the galaxies. So we better make sure that we understand that. And I think even though we've been conservative about our errors, the agreement with the JAGB and TRGB distances is telling us something. Those agree really very well. And there's an offset with the Cepheids, which I think we now need to really understand.
I think everybody would agree that each of these galaxies only has one distance. If you get differences in those distances, then there are systematic errors in one or all of those distance indicators.
Okay, so here are the measurements. So the green here is the JGB and its statistical uncertainty, and the red, that's the tip of the red giant branch, and the blue is the Cepheid measurement. And those, so the widths of the Gaussians are representing the statistical uncertainties in each of the methods. And the bars here are the systematic errors. And you correctly noticed that the Cepheids are larger, and partly that is we have a smaller sample right now, so that statistically the SH0ES measurement, I think, is much smaller uncertainty, but also all of these include the NGC 4258 uncertainty of 1.5%. That's common to all of the methods. But the Cepheids have additional uncertainty, as I said, with the period cutoff and metallicity uncertainty and reddening uncertainty, crowding correction uncertainty, and so on. It's larger than the other two methods. So the gray line here is just a frequentist estimate of it's the cumulative distribution of these PDFs, and the black line here represents a Bayesian estimate to the product of these PDFs. And that's what gives rise to these values shown here in terms of the overall value of the Hubble constant and the statistical uncertainty and the estimate of the combined estimate of the systematic uncertainty. And then if we compare that, we can look at the total uncertainty where we add the statistical and the systematic and quadrature, and so people tend to use one error bar. But as I say, we prefer to keep those separate. We think that's just more illuminating as to where the uncertainties lie at the present time. But if we do look at the total errors, this is the black line again, is the combined estimate for all three methods, and the blue dashed line here is for JGB and TRGB alone, which gives slightly lower as would expect. And just to finish up in terms of where we stand, if you look at the distributions that, here's the PDFs from Planck and DESI and our three methods, and then the cumulative, if this is what you started out with, then you wouldn't be saying that there is a tension. So our point is only at the moment, these are consistent with the standard model. We don't see this, again, extraordinary evidence that would push us all of these distances then to a value of 73 or 74. But the Cepheids still, our Cepheid data are consistent. We're seeing higher values. The Cepheids do give a higher value of H0, and I think it's going to take more time to understand, get to the bottom of these differences. but it's worth reiterating that the tip of the red giant branch and JAGB stars are away from the dust and away from crowding. As Barry pointed out, the tip of the red giant branch is physically very well understood, and these are less complex than the Cepheids. So I think in future we're going to see a lot more JWST data. I'm looking forward to LIGO data, eventually more data from neutron star, binary neutron star collisions. And this is soluble. But I think in the next few years with JWST, a lot of this is going to be a lot clearer.
When you say the blue line is the product of the other lines, I guess you don't mean literally the multiplicative product, because they've got the common NGC error, which shouldn't be. So you mean like it's like the product in a kind of statistical sense, not the multiplicative product.
Right, because they share that systematic. And they share an uncertainty in the 0.2 in that calibration. Yeah.
Yeah, the thing that, I mean, the reason we're having this talk is I actually reached out when you published the JAGB paper about having a talk on that, and then it got mentioned that this summary paper is also coming out soon. But that JAGB one seems very crucial to the story one tells about the Hubble tension, almost as a tiebreaker, right? Because the TRGB, and this is what I was always telling people when they were saying that your TRGB result is consistent with Planck. It's like, well, it's also consistent with SH0ES. So if one has a neutral prior, then it's not really telling you anything. It could be that SH0ES was correct and there's new physics, or it could be that Planck is correct and one has to just, TRGB will eventually fit on one of those two stories. But the JAGB is not consistent with SH0ES, right? Like it's if you look even at this plot here, it's if SH0ES is showing up at like 73 with a very narrow plus or minus kilometers per second per megaparsec, then it's not that consistent with JAGB. So then the story one actually starts to tell is, okay, TRGB is consistent with JAGB and Planck, but SH0ES is the kind of outlier. Yes, it's consistent with TRGB, but so what if it's not consistent with JAGB as well? So it does seem like the story one would tell before and after the JAGB method got published is a different story.
I think that's fair. And I think, whether you would take the difference between the JAGB and TRGB H-naughts is significant. They certainly are very close. And, again, they are consistent. So, the four of them are consistent.
Sure. I mean, on this plot, they don't look inconsistent at all, right? The red and green are very much overlapping. It's the green and not this blue, but the SH0ES blue that would not overlap.
The SH0ES blue. That's right. And I think, so what we need to understand is, are the uncertainties at the current time represent, do we have the data that we need to get a 1% value of the Hubble constant, which is the SH0ES estimate? It's 1%. And I think what we would say, and having been more conservative, is there are a lot of steps along the way, beginning with the anchors, beginning with how do you measure Cepheids, and how do you estimate metallicity, and how do you do crowding corrections and rending corrections and so on with the Hubble data that are that crowded. And then you tie into the supernovae and you have different calibration issues. So every step along the way, right, if you have a 3-step ladder now, the nearby anchors, the intermediate region where you can have HST and JWST, and then the more distant galaxies, you have to, the cumulative error has to be under 1%. And I think, if you look carefully at the data and analyze, what are the uncertainties at every step, it's hard at this point, I think, to make the case that we really have a measurement that is 1 in a million chance of being wrong. When you look at the challenges in doing photometry, particularly, when you pushed Hubble to its limit, it's hard. So, maybe it will come. We are consistent with there being a tension. I mean, there's no question.
Yeah, although, I mean, looking at your blue plot, it doesn't have that much residual weight at above 72 for H0.
Just to review the major points, I think JWST really is going to change our views of measuring distances to galaxies. It's a very powerful tool, and it will let us get to these questions of systematics. And it's only so far the nearest galaxies that have been observed, and it's really the more challenging ones that remain to be measured, and we'll see how those come in. And what we've done is to use these three different independent techniques, which, as we've shown, have based on very different physics. They're located in very different parts of the galaxy, and the two that now are giving agreement in the distances at the 1% level are the two that are out in the halo or the outer disk, where you don't have the severe systematics that you do with the Cepheids, and they also are a JWST calibration alone. You don't have to use the Hubble data at all. So the Cepheid distances are smaller, and they lead to a larger Hubble constant. They're currently the outlier. And if you tie into the type 1a supernovae, we're finding a value of just shy of 70 with statistical uncertainty of 1.05 and a systematic uncertainty of 1.12. And what we would say is that, we're not saying that there is no Hubble tension, but the results are certainly consistent with Planck and with lambda CDM cosmology, and there's no real pointing at this point to the need for additional physics.
Yeah, I feel like at the very least there is still a Cepheid tension. Like, no one has sat down and said, this is the exact mistake being made in the SH0ES analysis. Like, once you correct this, their value drops to 69, mission accomplished, move on. Like, there's still something going on, either with fundamental physics or with the Cepheid method, that needs understood.
Yeah, and as I say, we agree with the SH0ES distances on average. So it's there's nothing that we've seen that any group is doing wrong.
With these three methods, what is the one that has the best long-term prospects for getting out to higher redshifts to have even more supernova to calibrate against?
That would be the JAGB. Now, you could, in principle, go farther out with Cepheids, but that's, as we've seen, because you need to get periods for the Cepheid. So JAGB you can take out much farther with JWST. You need Hubble to discover the Cepheids and discover Cepheids in galaxies. The amplitudes are too small to go too far out.
And what are the kind of distances or even redshifts that one would be talking about with the upper limit of JAGB with JWST in say the next 5 or 10 years?
I think easily you get to 60 megaparsecs, and I think you could push it to 100 at sort of level of the coma cluster. That would be feasible.
With your Cepheid measurement, is there scope over the next couple of years to shrink your error bars? Because at the moment, your Cepheid measurement is very much consistent with SH0ES, but also because it's got quite wide error bars, very much consistent with TRGB and JAGB. Could you, over the next few years, shrink those error bars and see whether it ends up staying with SH0ES or moving with the rest?
Absolutely. So, that is our plan. We need more data on the calibrating galaxy, NGC 4258, and we will get that. And we need more galaxies. And, and what you really want are really good colors and really good luminosities and large enough samples. And that's all doable, and that will happen in the next few years.
Yeah, so I was going to ask you to put your serious observer hats on and then crazy theorist hats on. And with the serious observer hat, I was going to ask, what do you think might be the cause of Cepheids being high?
I would suggest that crowding is going to turn out to be the major issue. It is the only thing that is known to be a function of distance. It is also an extremely large error that has to be done in a statistical way when it's actually a systematic error. And it is solely the Cepheids that are most impacted by that.
I should admit that there is a talk on this channel called, I think the title is something like Cepheids are not the cause of the Hubble tension. Crowding is not the cause of the Hubble tension. But this is 4 years ago, and I have no memory of exactly what it was that they did, but it was Adam Rees giving the talk. But what he did that made that claim, because I'm not an expert, this was 4 years ago, but I guess they believe that they have it under control.
The nearest galaxies have been tested, and there's one galaxy at 40 megaparsecs that's been looked at, but most of them are nearer, and they're the easier ones to measure. So I think, it behooves all of us to make sure that these tests get carried out in the more distant sample, which is where we're seeing differences in the supernovae and where potentially they could have a problem with H0 at the larger distances. So, again, this will get done. It just hasn't been done yet, and we'll see where it lies.
Is there anything else that you feel is like the leading potential cause of it?
I would say, I think crowding is still a concern, and then what happens is that if you get the crowding corrections wrong, then you get the corrections for dust wrong, then you get the metallicity correction wrong. So crowding by itself is not going to be the answer. I mean, it's not by itself, but these effects are covariant. You get the colors wrong, you get the reddening wrong. And so this needs to be done in a self-consistent way, and we just need to make sure that you have accurate enough photometry to have a 1% measurement. And right now, for those distant galaxies, I would not be able to say that we can do 1% photometry at those distances at that resolution with the numbers of the area in 1 pixel that could be contaminating those Cepheids. I think it just remains to be established that you can do that to 1%.
We thought that by going to the infrared, we would reduce the reddening, which is true, that we would reduce the amplitudes, which would make things easier to observe on just with a couple of data points, and that crowding would be less, because we thought that Cepheids being in the disk, being near the origins of their birth sites, that most of the crowding would have been coming from O and B stars, which are blue. And as you go to the red, those stars would fade away and you'd have a nice smooth background. That proved to be totally wrong when Spitzer started analyzing nearby galaxies, and people had no idea about the presence of AGB stars that were enshrouded and weren't seen in the optical, even in the I band. And when you got past about 1 micron, these things just came roaring up all over the place. And they are point sources, and they are crowding sources of crowding. And so this was a real disappointment and real challenge, which was never anticipated. And I think we're still seeing the effects of that people didn't realize that what they were going to have to deal with in a new source of crowding, not just the old-fashioned blue star stuff.
If one wanted to say, okay, the expansion rate is 69, 68, 67-ish, but the cause of the Cepheid tension is not systematics, but some new fundamental physics. Do you know of anything that could be going on, like with the way gravity works on small scales, or some other new physics that might be responsible for the Cepheids, or is this just like I'm being silly?
No, I mean, talk about masses, and I think the favorite of Barry's, of what you could do with Cepheids that we're not considering right now. What types of things could enter into the Cepheid calibration, the unknowns that we're not even talking about right now. And I think there are many.
We have no idea what the impact of mass loss on Cepheids is. We almost certainly know that some of them are losing mass. Maybe not all of them, but maybe it's a stochastic process. Maybe it's something that is itself dependent on metallicity. Maybe it's not. But all of these things could be happening in the Cepheids, and we would be totally ignorant of it.
Or maybe we're not totally ignorant in the sense that we're now measuring it with your Cepheid measurement and the SH0ES measurement.
We're measuring it.
Yeah, again, we're using astrophysical objects, right? And they're, we may not understand all aspects of their evolution yet, and this would be a way of getting at it, right? Comparing with different methods and seeing, maybe we don't understand Cepheids as well as we think. And again, to come back to the point, we understand them now at the few percent level, right? These things are actually agreeing pretty well, even though there are these discrepancies. This is new for this field. We used to be talking about factors of 2 not that long ago. So the precision and accuracy has been steadily improving. And, maybe when we get to this level, we're learning new things. It might be astrophysics and not cosmology, and we'll see. I think, I think people need to remain open. I mean, I think we all need to remain open at this point, right? Open to the possibility that Lambda CDM, that there's something missing, and open to the possibility that it really maybe things are quite consistent. And I think things are going to resolve pretty clearly in the next couple of years, and JWST will let us get there.
Awesome. Yeah, like seeing this resolve would be great, even if it is just resolving to learn that Lambda CDM has survived again. What work being done in cosmology at the moment do you think is particularly interesting but underappreciated by the rest of the community?
I think that, I really like the gravitational wave siren stuff, and I think right now people aren't paying attention to it just because there's only one object. So I could look forward in future to there being more objects, because my feeling is that we need many methods, each with a high internal precision, to get to the bottom of this. And the fact that that's completely independent of the local distance scale and all of the kinds of challenges we've been talking about is really important. I also think that it's important for to be thinking about other kinds of models beyond Lambda CDM. I don't think that's popular at the moment. But we don't understand the fundamental model. And I think it's something that is a huge challenge. We don't know how to explain dark energy. I think it's one of the reasons why people are so enthusiastic about a Hubble tension, is that there's no way right now of explaining the standard model. It's a mystery.
Yeah, I feel like the Lambda and the CDM are a bit different in that regard. The problem CDM has is that there are far too many compelling models, and you just don't know which compelling model to pick. The problem that Lambda has is that there are no compelling models. Like even just the cosmological constant is compelling as a model, but then the value you have to give it is very uncompelling. So
yeah, so are we looking at the whole problem in the right way? And I think we just don't know that yet.
It seems to me that we really would, as a community, be so much better off if we had a settled value for the Hubble constant and use that in a way that we could go on to understand other things that depend on distance, like the total luminosity of this, the absolute magnitude of that. And maybe that way we will get somewhere on understanding dark matter. And by constraining the distance, people thought that they knew the Hubble constant from looking at the X-ray properties of clusters of galaxies. What they found out was they didn't really understand the X-ray properties of galaxies. And once they understood that there was something else there, they realized it was not a good distance indicator, but if you had given me a Hubble constant, I could have told you a great deal about the evolution of the gas in clusters of galaxies. So my hope is that we can get the Hubble constant behind us, not because it's in tension with anything, but because it's worthy of being settled for its own value. And I think we can do that locally.
Great. Thanks everyone for watching. If you like this, please do subscribe and click the bell if you want to be notified of new videos, and click like to help with YouTube algorithms, both for you and the channel, because you'll benefit, because YouTube will know to recommend more stuff like this. If you have any questions or suggestions, leave a comment. Otherwise, if you're watching this in the next couple of days, maybe check out a talk by the SH0ES team from a year or two ago. It was when they first reached the kind of their claim of 5 sigma. If you're watching this next week, check out the Abigail Lee's talk on the JAGB method that was talked about in this talk, but in more detail in that one. And thanks, Wendy and Barry, for the great talk.
Thank you.
Thank you, yes.